Hey everyone, today I'll be going over a Leetcode problem 72, edit distance. This is a hard Leetcode problem. You're given two words. Return the minimum number of operations required to convert word 1 to word 2. Each operation you can either insert a character, delete, or replace a character, right? So basically you go character by character, and like if they don't match up, you can insert, delete, or just replace it to another one. So this one, minimum, as you can see intuitively, if we actually take this test case here, just intuitively you can say, well, it has 3 characters, this one has 5. So if we want to convert word 1 to word 2, we know we're going to have to delete some, right? So we have ROS, so we can delete a few here. So we know that we just want the ROS. So if we delete the H and the E on the end, it'll be like ORS or whatever. Or actually, if we like go, what is it, like HRS or something like that, then you get the point. That's one or 2 operations because we deleted 2 characters. And then we can like, insert an O here and then take out the H. That's 4 operations, right? That's not even the minimum. The minimum is 3. Yeah, it looks like they replace H with R, remove R, and then remove E. Yeah, you get the point. So intuitively, a naive way to do this is you could go through the string and just make 3 choices, right? Either insert, delete, replace, or like do nothing. And you could do this and like backtrack through and like recursively generate like all possible scenarios, but that's very expensive. So what you can use is you could use dynamic programming, right? And all dynamic programming is just a way of storing subproblems, building on top of them, and getting to like a solution, as long as you have some base truth. So we have these words, right? And we get to make a decision at each character. Now I'm going to explain kind of how you model this as a dynamic programming problem. So here I have like a matrix. We have horse and ROS. This is this first example here. So we model it like a matrix, and that's exactly how we're going to solve this, a DP matrix. And we go through each one. And we want an empty character here. We have to do that because basically we need to have like some base truth, right? So at an empty character, an empty string, it's just 0 because they're already equal. There's 0 operations needed for that. For the H, so basically how this works is we compare the letter in this with the letter in the other one. So, or the substring in the other one. So this is like the string prefix. So H with empty, we have to add 1, and it just goes through all the way through. Now, basically the reason why this is because we're comparing horse with just an empty string. So we're going to have to add 5 characters or delete 5 characters to make it equal. So now we do the same also on this column here, because this would be ROS compared to with an empty string. So now here's where it gets tricky. So this is where dynamic programming becomes very, very friendly, because we can actually build on this base truth. We have this base truth now. Let's build on top of it. So what we want to do is we want to compare these characters here. So we compare the H with the R. So if we think this is comparing string H with string R. So we're going to have to replace 1 character. So when they're not equal, what we do is we get the minimum of the adjacent columns and we add 1. So we get this one here, and we see the minimum is 0 of the adjacent, and we add 1. So it's just 1 here. The reason being is we don't have to delete, we don't have to insert, we can actually just replace. So the reason why we can go up to the top left and make it equal to this is because we could just replace one of the characters and make it equal to this one. But that replacement is a step, so we have to do the minimum plus 1, right? So here we get to R and O. They're not equal, so again, minimum. And if we actually look here, it would be HO and R. So minimum of these plus 1 would be 2. And that's because, again, we could just replace and like delete or something like that, right? So then I'm just gonna scribble this out. I don't know how to erase on this tool. So yeah, R and R are equal. So now when you get here, they are equal. So we can actually just take the adjacent here, or the top left. So this would just be 2. The reason why we can do this is because they're equal, right? So it's going to be the same exact amount of operations as whatever was on the top left, because this didn't change anything. They're equal. it won't require any other operations. So we just take the top left. R and S, minimum plus 1, minimum is 2, 3, E and R don't match, minimum 4. And then we get to O and H, same thing, minimum plus 1. O and O are the same, so we get the top left, go back to 1. R and O are different, minimum plus 1. S and O are different, minimum plus 1. E and O are different, minimum plus 1, 4. H and S are different, minimum plus 1, which is this 2. That becomes 3. O and S are different, minimum plus 1. There's that 1 here, so we go 2. R and S are different, minimum plus 1. That's 2 again because we have this one. S and S are the same, so we just take the top left, 2. And then E and S are different, so we take the minimum plus 1, which is this 2 here. That becomes 3. And this is our result. Why? Because we used every other subproblem in both of these strings to build to this point. And that's why this works. I just wanted to explain the intuition behind it and why it works, because the actual code is pretty simple. So let's go ahead and create a DP matrix, and let's get these dimensions really quick. So I'll just call M of the matrix word1.length, and N will be word2.length, right? So then we're going to set up our DP, which is just going to be a 2-dimensional array, and we're going to call it a new integer array. And we're going to give it the dimensions of M and N. And we're actually just going to go M plus 1, N plus 1, right? So what we really want to do is plus 1 here. The reason why we do this is remember that empty space, right? Going back to our whiteboard here, we have to have this empty space because of these base truths here. So we're going to go plus 1, yeah. So what we have to do first is we have to do this logic here. See this 0, 1, 2, 3, 4, 5 and this 0, 1, 2, 3. Let's just fill these out. That's easy. So let's actually go through just all the i's. So this would be word1.length and then I++. And then this would actually be, so if this is word1 and then this is M, this would actually be all of the rows, right? So we'll go all of the first elements in the first rows. So basically DPI of 0, so the first one there, is just going to be equal to the last one. So we're going to go, actually, what we can do is we can start at this because we know that first one's 0. And then we can go DPI at 0 plus equals DPI, or actually, sorry, I'm so sorry. This could just be equal to I. Okay, so everything's good there. Let's actually copy this down. And this is going to be the same thing, but now going to go through that first row. So this will be J, and we'll just name this J for readability. This will be less than word2.length. So word1 is like row-wise, and word2 is column-wise, right? Or the other way around. So then the next thing we want to do is just iterate through the rest and do the same exact logic that we were talking about before. And we don't even need this. I got the dimensions for a reason. So let's make this as clear as possible and go like that. Okay, so moving through here, we have I is less than M, and then moving forward like such, let's go ahead and go in J is equal to 1, J is less than N, and then J++. So then now what do we want to see? We want to make sure that the characters are equal at this point. If they are, you remember what we do, we just take the top left, right? So basically, if word1.char at I is equal to word2 char at j, this means we take the top left, right? So dpi at j is just going to be equal to dpi minus 1, j minus 1. And this is another beauty of why we did this empty string as well. Because if you think about it, we'll never get an out of bounds. Because we can do this I minus 1 and j minus 1 all day long. We don't have to worry about bounds checking because we're just starting from 1 and 1. We already pre-calculated everything else. Else it means they were not equal, so we actually have to get the mins. So I'm going to do that now, and what we're going to actually do is we're going to take the minimum of dp at I minus 1 and j minus 1, and then we're going to have to like nest this. So then we're going to take the minimum of dp at I minus 1 j and the dp at I j minus 1. So all this is doing, this looks funky because we have like nested math mins or whatever, but all this is doing is just getting the minimum of the left, the top, and the top left, right? So it takes the minimum of these, then it compares it to this one. So yeah, so then this is the minimum, and we're going to set the dp to be 1 plus min. Why do we do that? Remember, we must use an operation here because the characters are not equal. We don't care if it's insert, delete, or replace. We just know it's going to require one operation. So then we get the minimum. So the minimum subproblem, we build on top of it, and we go 1 from there. Then last, what we can do is we can simply return n minus 1, n minus 1. So just getting the bottom right one, right? The very last element. Let's go ahead and run this, see what happens. And cannot find a symbol. That is lovely. That's because I named that I. Let's go ahead and run this again. And I did the I++ there. Sorry about that. Let me run this again. And yeah, it's going to time out. Okay, here we go. And looks like we get an index out of bounds. Oh yeah, that's because we actually have to go I minus 1 here, right? And that's because technically we made the strings bigger than what they are because of this empty string, so we have to, index these. So then lastly, okay, let's see what happens. Let's run this again, and we get accepted. Let's submit it. And very slow. Yeah, but anyways, this is how you do it using just tabular DTP. I'm going to talk about time and space. Time is actually, it's O of m times n, where m is the length of word 1, n is the length of word 2, because we have to go character by character, compare them all, right? So it's actually this is you could say n squared, if you want to be technical about it. Space is the same exact thing, right? Because we have to build a DP array that's the same exact dimensions. So yeah, hopefully this made a hard problem kind of easy. I didn't want to overcomplicate it intentionally. So yeah, thank you for watching. I appreciate it.